Hello there, and welcome to the Ancient Historian, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're not racing through the present, or charting the known boundaries of the world. Instead, we're leaning back, letting questions drift into the dim corners of imagination, and asking, what if the Earth were not the vast round sphere we know it to be, but flat? Picture it for a moment. For centuries, stretching back to at least 500 BCE, philosophers and travelers debated the shape of our world. In 350 BCE, Aristotle stood beneath the Mediterranean skies and argued the Earth was round, pointing to the curve of the lunar shadow during an eclipse. By the year 240 BCE, Eratosthenes, with nothing but shadows and clever thought, calculated the circumference of the Earth with astonishing accuracy. And yet, despite thousands of years of evidence, the idea of a flat Earth lingers like a ghost of an ancient story hovering at the edges of belief, whispering possibilities that twist against the fabric of what we know. If this kind of quiet, wandering question stirs your curiosity, I'd love to hear from you. Drop a comment below and share where you're watching from, and what time it is there right now. It's incredible to imagine people all over the world, from the flickering lamplight of one city to the midnight hush of another, each following the same trail together, like scattered sparks tracing the edges of history. And if you feel drawn in, tap like or subscribe. It helps this little signal ripple outward, reaching other curious souls moving through the night, like shadows chasing sunlight. No pressure though. Think of it more like a soft invitation, a drifting feather that lands without a sound, or a faint whisper carried by the wind, guiding us towards something unexpected. So settle back. Let your thoughts stretch out like a map across the centuries, from the first sailors of the ancient seas around 1000 BCE, to the voyages of explorers in the 1400s, to the quiet hum of the modern age in 2025, where questions both old and strange still circle back to us. Tonight, we ask not as scientists looking for proof, but as storytellers wandering through possibility. What would happen if the Earth were truly flat? Imagine waking up one morning to a world that looks almost like the one we know, yet subtly off. The ground beneath your feet feels normal at first. The wind brushes your face as usual, but the rules that govern movement, air, and water are entirely different. Gravity, the invisible force that has always seemed to pull us straight down, no longer behaves as you expect. On a flat Earth, gravity would not tug evenly toward the ground beneath you. Instead, every object, every drop of water, and every breath you take would be pulled toward the very center of the disk, the Arctic region, the heart of this cosmos. As you walk further from the center, the pull grows slanted, tilting objects subtly, like trying to balance on a gentle slope that never ends. Imagine trying to pour water on the edge of the disk, and watching it slowly creep and drift inexorably toward the center, as if the land itself were alive and slurping everything toward one central point. And water, as it always does, would collect in the lowest gravitational basin, the center of the flat Earth. Oceans, rivers, lakes all forming a massive swirling heart at the disk's core. The atmosphere, too, would pool at the center, becoming denser, almost suffocating for anyone daring to live near the Arctic heart. At the outer edges, the air thins until it disappears entirely, leaving vast frozen plains of emptiness, uninhabitable and silent. The edges would be frigid and barren, an endless wasteland where no bird flies, no tree grows, no human could survive. Step too far, and the very air would abandon you, leaving a vacuum-like emptiness stretching toward the ice-encrusted horizon. Now consider the magnetic field, a subtle force that shields life from the sun's relentless radiation. On a spherical Earth, this field is generated by the molten core, wrapping the planet in invisible armor. Strip that core into a flat disk, and the magnetic field vanishes. Without it, the solar wind, a constant stream of charged particles, would gradually strip the atmosphere from the surface. There would be no northern lights dancing in the sky, no auroras shimmering in green and purple. Those beautiful, silent curtains of light are a product of a round Earth's magnetic shield. A flat Earth would leave the skies dull, unprotected, and lifeless. And yet, the atmosphere itself would behave strangely. Dense at the center, vanishing at the edges, it would create unpredictable weather patterns. Winds would sweep toward the core, carrying snow, rain, and clouds like rivers of air. Hurricanes might spiral outward from the center, instead of across the globe. Storms would be concentrated in unimaginable ways, and the temperature differences would be extreme. Unbearable heat near the center, frozen desolation at the periphery. Every step away from the Arctic hub would feel like a journey into a new climate, as though nature itself had been divided, section by section, along the disk's curvature, or rather, the lack of curvature. Gravity, atmosphere, and water are the pillars of life, yet on a flat Earth, they conspire in ways that make survival a constant struggle. Objects would drift toward the center. Oceans would heave unnaturally. Air would thin into nothingness at the edges, and the shield that protects all living creatures from the sun's fury would be gone. Life would cling desperately to the center, crowded into a single sprawling heart, while the rest of the planet would remain eerily empty, silent and frozen. Now imagine looking up at the sky on this flat Earth. The sun doesn't rise and set in the familiar arc we've known for millennia. Instead, it hovers, a glowing disk above the flat plane, circling endlessly over the land like a lantern on a giant invisible turntable. There is no sunrise or sunset as you know it. Instead, the sun spirals in tight loops over the center of the disk, its light stretching farther than your eyes can follow. Shadows behave strangely, bending in ways that make your familiar sense of direction unreliable. In some places, the sun seems almost directly overhead at all times, never dipping below the horizon, while in others, far from the center, the light barely touches the ground, leaving stretches of eternal dimness. Time zones, those invisible markers of human order and convenience, lose all meaning. On a flat Earth, the sun is not a distant star circling a globe. It is a close, moving light, casting uneven illumination across the land. Noon in one region may feel like midnight in another, and no seasonal changes would occur as we understand them. Winter and summer, spring and autumn, all arise from the tilt and orbit of a spherical Earth, the angles at which sunlight meets the surface. Remove the curve, remove the tilt, and the world becomes unchanging in one sense, but chaotic in another. One region bakes in relentless light, while another languishes in unbroken shadows, creating extremes of temperature, weather, and daylight that humans and animals would struggle to adapt to. The sun's path also affects tides. Without a rotating spherical Earth, the ocean's behavior becomes alien. Water pulled toward the center by gravity pools in the Arctic heart, but the sun's spiral above creates heat patterns that churn the seas unpredictably. Waves may slam outward from the center, sweeping land in currents that feel alive, as though the ocean itself were aware of the flat Earth's shape, and responding to the sun's path with violent rhythm. Coastal areas experience light and darkness in ways that defy expectation, and the tides no longer follow the gentle lunar pull that humans have learned to predict. They surge and falter in patterns that make any simple calendar useless. The flat Earth sun would also make the concept of seasons meaningless. Fields do not grow in cycles dictated by a predictable tilt of light. Crops would either wither under unrelenting brightness, or fail to sprout in permanent twilight. Animals that rely on seasonal signals, migrating birds, spawning fish, hibernating mammals, would lose their internal compass, struggling in an environment where light no longer maps onto time. Human societies would have to invent entirely new methods of measuring days, months, and years, constantly recalibrating as sunlight spirals in inconsistent paths. And imagine the psychological effect. Standing under a sun that never truly rises or sets, your body clock thrown into confusion, your sense of order disrupted, life would feel disorienting. Even simple concepts like morning and evening, work and rest, would become fluid, uncertain, and unreliable. Ancient humans relied on the predictable cycle of night and day to organize survival, migration, and hunting. On a flat Earth, that rhythm disappears, leaving patterns of light that are uneven, looping, and sometimes cruelly contradictory. Without a spherical rotation, phenomena like eclipses, seasonal constellations, and predictable weather patterns vanish. Stars might appear fixed or swirling unnaturally above the flat disk, and the moon's phases would be incomprehensible. Night would not blanket the world uniformly. Instead, patches of darkness and light might coexist, creating surreal twilight zones where shadows intersect in impossible ways. Everyday life, navigation, agriculture, and the very passage of time become a challenge. Human perception, tuned over millennia to a globe spinning through space, would find no comfort in familiar markers. And the animals, those natural timekeepers of the earth, would struggle even more. Migratory birds might fly in endless loops. Wolves howl at suns that never set, and nocturnal creatures could find themselves lost in permanent ambiguity. The spiral sun above a flat earth is not just a curiosity. It reshapes every aspect of existence, bending light, time, and perception into a reality utterly alien. Shadows stretch and twist, days blend into days, and the very sky becomes a theater of strange and unpredictable illumination, leaving life to adapt or fail in ways no one has ever imagined. Step into this flat world and consider the ground beneath your feet. On a spherical Earth, tectonic plates slowly drift, collide, and slip beneath one another, sculpting mountains, carving valleys, and triggering earthquakes with a rhythm that has shaped life over billions of years. But flatten the planet into a disk, and tectonics as we know them vanish. There is no molten core spinning, no mantle convection driving plates across a globe. Mountains would rise, if at all, not from the slow push of colliding plates, but from entirely different, inexplicable processes. Volcanoes might exist only as curiosities, local anomalies rather than features of a planet with deep inner heat cycles. Earthquakes, the familiar tremors that remind us the planet is alive, would become chaotic and unpredictable in nature. Some regions might feel unnaturally stable, frozen in place by the lack of plate dynamics, while others could erupt with inexplicable tremors as stresses accumulate in ways foreign to physics as we know it. And then there's visibility. On a globe, the curvature of the Earth hides distant objects. Mountains vanish over the horizon, ships disappear hull first into the sea, and even the tallest structures fade with distance. Flatten the planet, however, and the rules of line of sight change dramatically. Stand on a hill, and you could see landmarks hundreds or thousands of kilometers away, across plains that now stretch uninterrupted. A mountain that once disappeared over the horizon becomes a beacon in the distance. Cities could be seen from unimaginable distances, coastlines stretching endlessly into one another. The human experience of the world would shift. Travel might seem shorter or stranger as familiar landmarks remain visible far longer than expected. Shadows of distant mountains would creep across valleys in ways that are almost eerie, and the world would feel unervingly open. Every landmark a constant companion on the horizon. Satellites, too, would be impossible. GPS, weather forecasts, global communications, all the invisible web connecting the modern world, relies on objects orbiting a spherical planet. A flat disk cannot sustain orbit. Rockets fired into space would either crash back to the surface or drift off into an infinite void without returning. Communication satellites, television signals, and internet beacons that circle the globe would vanish. Navigation would regress to methods as ancient as the stars. Compasses unreliable, maps limited. Weather forecasting would become an exercise in intuition and observation alone. Storms, hurricanes, and other atmospheric phenomena would be far harder to track, making modern society's precision practically impossible. The consequences ripple into every aspect of life. Human expansion and civilization would be constrained. Cities built without the advantage of distant surveillance or accurate navigation. Global trade would stumble, reliant on guessing the position of far-off ports. Exploration becomes a daring game of uncertainty, where the risk of missing landmarks or wandering into inhospitable zones is constant. Even flight would be a complex puzzle. Aircraft rely on GPS and a spherical model of the planet to navigate. Without satellites, planes might fly in dangerous loops, encountering unexpected terrain or weather patterns, and pilots would have to rely on ancient methods of dead reckoning in the stars. And yet, despite these limitations, life adapts. Humans find ways to measure distance with triangulation, to predict storms with barometers, to chart rivers and mountains on foot and by compass. But the natural world remains stranger than fiction. Water behaves differently, pulled toward the Arctic center, creating oceans that swell unnaturally. Winds follow patterns shaped not by rotation, but by the density of air at the center and the thinning vacuum at the edges. Mountains loom taller or smaller depending on their position relative to the center, and the horizon stretches unervingly flat in every direction, making the planet feel infinite in a way that is both thrilling and disorienting. Even the stars behave differently. Without a rotating globe beneath them, constellations would shift in unexpected ways, drifting across the flat sky in patterns that defy the rhythms humans have relied upon for navigation for thousands of years. Nighttime would be confusing, celestial markers would lose meaning, and explorers would constantly recalibrate, trusting their eyes over centuries of learned methods. On a flat Earth, tectonic processes, visibility, and satellites intersect to create a reality where the familiar becomes alien. Mountains, landmarks, and horizons behave in ways that challenge perception, while the modern conveniences that tether humans to precision vanish. The world becomes a strange, open expanse where observation, intuition, and adaptation are the only guides across an endlessly flat and unpredictable plane. Step out to the edge of one of the oceans on this flat Earth, and the world changes in ways you've never imagined. Water, which on a spherical planet pools due to gravity toward the center of the globe, now obeys an entirely different rule. Gravity pulls everything toward the Arctic center, and the oceans follow suit, forming a colossal, swirling heart at the very center of the disk. Waves crash and spiral inward, currents moving like rivers toward the core, and any water on the outer regions creeps relentlessly back toward the Arctic hub. The familiar ebb and flow of tides, dictated by the moon's pull and Earth's rotation, is replaced by chaotic movement, unpredictable surges and currents that challenge the intuition of any sailor brave enough to venture far from the center. Coastal life becomes an exercise in adaptation. Fish and marine mammals congregate near the center, where water is deepest and most stable, while the edges remain frigid, nearly lifeless. Coral reefs, if they can even exist under these strange conditions, cluster tightly around the center, creating dense underwater cities of color and life in a concentrated, almost claustrophobic heart of biodiversity. Out toward the periphery, the sea is thin, shallow, and ice-encrusted, a frozen desert where nothing thrives. Currents sweep outward erratically, and storm surges can tear along the flat plain with destructive, unexpected force. The surface of the oceans behaves like a distorted mirror, Waves radiate in curves dictated not by tides, but by the invisible pull toward the Arctic hub. Imagine watching a ship sailing across the ocean. It never disappears over the horizon as we know it. It remains visible until it reaches the central ocean. And yet the water itself behaves strangely, with tides heaving toward the center and forming giant swirling vortices. Cyclones and hurricanes no longer spin along predictable paths, they gather around the central ocean, spiraling in patterns dictated by the dense pull of gravity toward the Arctic, forming massive, almost permanent storms that dominate the region. Even the moon and the sun influence the water in ways unfamiliar. Without the planet's rotation, the usual gravitational interaction that creates daily tides is gone. Waves would rise and fall only in response to local variations in gravity and wind, creating unpredictable flooding and dangerous conditions along coastlines. Rivers pouring into the central ocean might form enormous deltas, their currents clashing and twisting as water from different regions converges. Islands far from the center might be isolated by expanses of unnavigable, frozen water, effectively trapping life in pockets along the periphery. The atmosphere above the oceans also behaves strangely. Near the center, the air is dense and humid, holding clouds low to the surface, pouring rain in near constant sheets. Toward the edges, air thins almost to nothing, creating sharp gradients of pressure that whip winds across the flat oceans with terrifying speed. Storms move in unexpected directions, and the very motion of waves seems influenced as much by air density as by water itself. Sailors, navigating this world, must constantly read both the sky and the water, attuning themselves to subtle shifts that might indicate an approaching surge or sudden vortex. And consider the temperature distribution. The center of the ocean, under constant light from the spiraling sun, may be warmer than any sea we know, while the edges remain frozen, with giant sheets of ice extending endlessly. Currents carry heat inward, creating chaotic mixing zones where warm and cold water collide violently. Life at the boundary struggles. Species must adapt to sudden changes in temperature, salinity, and oxygen levels. Giant predators might patrol these strange borders, hunting in the swirling currents of the central ocean, while tiny creatures thrive only in narrow, stable zones. The flat Earth oceans are both alive and alien, responding to gravity, sunlight, and wind in ways impossible on a globe. They twist, surge, and spiral, forming currents and storms that seem almost sentient. Coastal communities, if humans were to exist far from the Arctic center, would experience extremes that no sailor, no civilization, and no ecosystem has ever faced. Life clings desperately to predictable zones, leaving the outer reaches of the ocean silent, frozen, and perilous. Now picture traveling outward from the central heart of the flat Earth, following the pull of gravity and the swirl of oceans. As you move further from the center, the air begins to thin, and the warmth of the Arctic-centered sun diminishes. The atmosphere, once dense and protective near the hub, becomes fragile and sparse. Breathing grows difficult. The pressure drops gradually at first, then sharply, until it feels as though the world itself is slipping away. The edges of the flat disk are not merely cold, they are hostile. A frozen expanse where no ordinary life could survive. Every inhale becomes labor, every step a challenge as the wind sweeps across barren plains, carrying ice and dust in sharp, slicing gusts. The temperature difference is extreme. Near the center, warmth persists, currents and wind provide some moderation, and life finds a way to thrive. Yet near the edges, temperatures plummet to levels more extreme than any polar winter ever experienced on a spherical Earth. Snow and ice dominate. Glaciers creep outward in slow, unstoppable rivers of frozen water, and any attempt to settle or grow food is futile. Even the hardiest plants would struggle to root, and animals that venture too far are quickly trapped in the frozen wasteland. Storms here are not seasonal, they are permanent, relentless, and often violent, whipping thin air across frozen plains in blizzards that reduce visibility to zero. The edges are not only cold but perilously airless. The thin atmosphere provides minimal protection from the solar wind, leaving the land exposed to harsh cosmic radiation. Without the magnetic field generated by a molten core, the sun's charged particles bombard the surface, stripping away moisture and eroding the fragile top layer of the soil. Life here is a constant battle. Any creature that wanders too close finds itself struggling against radiation, frost, and a lack of breathable air. The edges of the disk are effectively uninhabitable, a no-man's land stretching toward the distant horizon, marked by silence, ice, and danger. The extreme environmental conditions create strange natural phenomena. Winds sweep in spiraling patterns toward the center, interacting with the frozen terrain to form massive ice cliffs, towering ridges and snow dunes that move slowly like desert sands. Clouds, sparse and thin, cast eerie shadows over the frozen plains, and the dim sunlight that reaches the edges casts long, distorted shadows, making the landscape feel vast and surreal. Visibility is deceptive. What seems nearby may be hundreds of kilometers away, and landmarks appear distorted as the air thins and light bends unnaturally through layers of cold, sparse atmosphere. Even water behaves differently at the edges. Any rivers or lakes are shallow, often frozen solid, and tidal surges from the central ocean reach these regions in strange, delayed patterns. Waves arrive at angles that make them seem almost alive, climbing ice ridges before collapsing in violent, noisy crashes. Coastal life is impossible. There are no fisheries, no marine mammals venturing this far from the central hub. The periphery is silent and barren, yet the dynamics of water, wind, and ice combine to create a harsh beauty and alien wilderness shaped by the extremes of physics on a flat plane. For any human trying to traverse these edges, survival becomes a relentless challenge. The thin air forces slower movements, higher energy expenditure, and careful management of oxygen. Food and water are scarce, and the constant wind chills any exposed skin. Navigation is disorienting. Without reliable magnetic poles or GPS satellites, travelers rely solely on visual cues, which are distorted by mirages and the long sightlines across the flat expanse. One false step could send a wanderer into a frozen wasteland with no return, a world where the pull of the center is their only guide. Even the climate itself is unstable. Snowstorms can form without warning, and blizzards sweep in with winds that twist unpredictably from the dense center toward the thinning edges. Atmospheric pressure is uneven. Pockets of rarefied air collide with denser patches, forming unpredictable gusts and violent whirls. Lightning strikes occur in odd patterns, and even the clouds seem to respond to the unnatural physics of this flat plane. The edges are a place of extremes where the world feels both alive and uninhabitable, where nature tests every attempt to survive against impossible odds. In this flat Earth world, one of the most invisible yet profound changes is the absence of a magnetic field. On our spherical Earth, the molten core spins deep beneath our feet, creating a protective bubble that shields every living thing from the sun's relentless bombardment of charged particles. The solar wind. Remove the sphere, flatten the disk, and that magnetic field vanishes. Suddenly, the invisible armor that has protected life for billions of years is gone, leaving the atmosphere vulnerable, fragile, and constantly under attack. The solar wind rips through the upper layers of air, stripping molecules and thinning the already unstable edges of the disk. The consequences are both immediate and subtle. Cosmic rays and high-energy particles strike the surface directly, altering the chemistry of water, soil, and even the cells of living creatures. Imagine standing on the edge of the flat Earth, feeling the icy wind against your face, while invisible streams of radiation wash over every inch of exposed skin. Life clings precariously to the center, where the atmosphere is dense enough to absorb some of the energy, but the outer regions are left raw and exposed. Even the simple act of breathing becomes dangerous at the edges, where the protective blanket of air is thinnest, leaving organisms vulnerable to both radiation and the cold. Auroras, those dazzling dances of color in the night sky, no longer exist. On a spherical Earth, they form when charged particles collide with the magnetic field near the poles, painting the sky with greens, purples, and reds. Flatten the planet, and these ethereal light shows vanish, leaving the night sky eerily uniform, a dark ceiling interrupted only by the scattered stars and the spiraling sun. For humans, this absence feels strange, almost spiritual. The magical living lights of the aurora are replaced by a stark, empty sky, reminding observers of the fragility of life without the protective bubble of the magnetic field. Radiation from the sun also affects weather in unpredictable ways. Near the center, dense air mitigates some damage, but storms behave differently under unfiltered solar energy. Winds gain intensity, clouds form in strange, dense patterns, and the oceans respond with unpredictable surges as radiation heats water unevenly across the disk. Farther from the center, the thin air offers no resistance, making blizzards and dust storms more extreme, their destructive power magnified by the lack of atmospheric shielding. The loss of the magnetic field has long-term effects on life too. Seeds exposed to high-energy particles mutate more quickly, potentially producing unexpected adaptations or catastrophic failures. Animals sensitive to magnetic cues for navigation, birds, turtles, and whales find themselves utterly disoriented, unable to follow paths they once traveled instinctively. Migration patterns collapse, hunting strategies fail, and entire ecosystems wobble on the brink of chaos. The flat Earth forces life to adapt in ways unimaginable on a round planet, with survival focused around the small, protected center where the pull of gravity and density of the atmosphere offer refuge. Human technology too falters under these conditions. Satellites cannot orbit a flat disk, and even terrestrial communication devices struggle in regions bombarded by radiation. Compasses are unreliable without a magnetic field, leaving navigation primitive. Attempts to generate power, predict weather, or maintain infrastructure face constant disruption, as high-energy particles interact with machinery, short-circuiting circuits and creating anomalies in electrical grids. Life depends on ingenuity, observation, and constant vigilance, a fragile balance on an exposed, flat world. Even oceans are affected. Water near the edges, unprotected from solar wind, evaporates more quickly, leaving saline crusts and barren landscapes. Currents shift unpredictably as uneven heating creates turbulence, while creatures in the center thrive in the relative safety of dense, buffered water. The central ocean becomes a hub of life and movement, while the edges remain desolate, frozen, and barren, threatened both by exposure to the elements and the absence of protective magnetic shielding. In short, the absence of a magnetic field transforms the flat Earth from a theoretical curiosity into a dangerous, uninhabitable, and alien world. Life, weather, and water all respond to forces we can barely imagine, creating landscapes of extremes, unpredictability, and tension. A place where survival is concentrated, fragile, and constantly tested by the sun's unfiltered fury. On a spherical Earth, the horizon exists because of curvature. As objects move farther away, the curve of the Earth hides them from view. Ships disappear hull first as they travel across the ocean, Mountain peaks vanish beneath the horizon, and tall buildings reveal only their highest floors from a distance. On a flat Earth, this curvature would not exist. Visibility would extend indefinitely across the surface, meaning in clear weather, one would be able to see for thousands of miles. A person standing on the coast of North America should be able to spot the cliffs of Europe across the Atlantic, and mountain ranges like the Himalayas would be visible from impossible distances. The lack of a true horizon would alter navigation, photography, and even the way humans understand distance. Every lighthouse, every tall structure, every city skyline would remain visible no matter how far away it stood. Astronomy too would be unrecognizable. Currently, the curvature of the Earth limits the portion of the night sky visible from each hemisphere. Stars rise and set as the planet rotates, and constellations vary depending on latitude. In a flat Earth model, the sky would be universally the same for all observers. Polaris, the North Star, would be visible even from the far south, a contradiction to reality where it sinks below the horizon once one crosses the equator. Celestial navigation would lose all meaning, as the map of the stars would no longer change with latitude or hemisphere. The horizon is also crucial for measuring Earth's size. Ancient Greek thinkers like Eratosthenes calculated the circumference of the Earth by comparing shadows cast in different cities. A flat Earth would erase such measurements, and the consistency of angles and distances would be impossible to reconcile with observed phenomena. Without curvature, surveyors and explorers would not need to account for spherical geometry. Yet everything from airline flight paths to tunnel construction depends on the reality of a round Earth. The issue of satellites creates an even greater contradiction. Today, satellites orbit the Earth because of gravity acting on a spherical planet. They provide global communication, GPS signals, internet access, and weather forecasts by circling the planet in predictable paths. On a flat Earth, orbit would be impossible. A disc-shaped world offers no closed gravitational field for satellites to revolve around. Instead, any launched object would simply fall back down or drift into space. There would be no international space station circling above, no satellite imagery of weather systems, no global communication networks, and no real-time tracking of flights or ships. Meteorology, global positioning, and even military reconnaissance would cease to function. The absence of satellites would also change daily life in subtle but profound ways. Smartphones would lose GPS navigation. Weather alerts would no longer arrive from space-based instruments. Television broadcasting would collapse without satellite relays, and long-distance communication would rely solely on cables and terrestrial radio towers. Space exploration itself would be halted, as spacecraft use orbital mechanics that only function in a spherical gravitational system. Astronomical telescopes in orbit, like Hubble and James Webb, would never exist, cutting humanity off from its view of distant galaxies. Even more fundamentally, the very photographs and live video feeds of Earth from space would be impossible. In the flat Earth model, such images must be dismissed as fabricated. Yet they remain some of the most consistent and verifiable evidence for Earth's roundness. Without satellites and orbital stations, there would be no explanation for how humans continue to send signals, track storms, or map the entire planet. The contradiction between modern technology and the flat Earth framework reveals itself most clearly here, where visibility, horizons, and orbital mechanics intersect. On a spherical Earth, gravity pulls equally toward the planet's center, creating stable oceans that wrap around the globe. Water naturally finds its level, forming seas and lakes that conform to the curvature of Earth. On a flat Earth disk, however, gravity would act very differently. Instead of pulling everything downward, it would pull toward the central point of the disk. This shift in gravitational force would cause all the oceans to flow inward toward the center, pooling in one enormous ocean that dominates the Arctic region. The outer edges of the disk would be left dry and barren, unable to hold water because gravity would not pull liquid outward toward the rim. Tides on our spherical Earth are caused by the gravitational interaction between the Moon, the Earth, and the Sun. The Moon's pull creates a bulge of water, which we experience as high tide, while the opposite side of the Earth also bulges due to centrifugal forces. On a flat Earth, such tidal behavior would not exist. If the Moon were present above the disk, its gravitational influence would not create the same bulging effect. Instead, any pull would likely drag water unevenly toward whichever side of the disk it hovered over, resulting in chaotic water movements that are nothing like the predictable ebb and flow we rely on. The consequences for navigation, shipping, and coastal living would be devastating. Ports and harbors would not experience stable tides that allow for predictable docking schedules. Coastal ecosystems, which depend on tidal rhythms, would collapse. Marine animals like crabs, mussels, and sea turtles, which rely on tides for their life cycles, would not survive. Ocean currents, such as the Gulf Stream, which regulate climate across the planet by moving warm and cold water around, would also cease to function. This would leave much of the disk world unbalanced in temperature, with the center flooded and humid, and the edges frozen and barren. The question of boundaries also arises. Flat Earth models often suggest a massive ice wall, commonly described as Antarctica, encircling the disk and keeping the oceans from spilling over into space. If such a wall existed, its structural role would be unlike anything in nature. It would have to be thousands of miles high, perfectly circular, and somehow unbroken around the entire disk to contain the massive inward pull of water. Without such a barrier, water would not only fail to stay at the rim, but would never reach it in the first place, since gravity would pull it all toward the center. Finally, storms and waves would behave differently. On our round Earth, the Coriolis effect, caused by rotation, shapes hurricane paths and large-scale ocean circulation. On a flat Earth with no spin, there would be no Coriolis effect. Storms would not spiral. Instead, they would move in chaotic, unpredictable patterns. This lack of atmospheric organization would lead to extreme weather events that are harsher and more destructive, making the oceans far more dangerous and unstable. Satellites are one of the clearest pieces of evidence supporting a spherical Earth. Yet, in a flat Earth model, they would not be able to exist in the way we know them. Satellites orbit the Earth due to the balance between gravitational pull and their forward motion. This requires a round planet with a gravitational center. On a flat disk-shaped Earth, there would be no central point of gravity to sustain orbital motion, making satellites impossible. Without satellites, countless aspects of modern life would change dramatically. Global Positioning System, GPS technology, which allows us to navigate with precise accuracy, depends entirely on satellites orbiting the Earth. In a flat Earth scenario, GPS would not function, leaving humanity with outdated methods of navigation, such as maps, compasses, and guesswork. Weather forecasting also relies heavily on satellites that provide images, track storm systems, and monitor atmospheric patterns. Without satellites in orbit, predicting weather events like hurricanes, tornadoes, or blizzards would be nearly impossible. Communities would be caught off guard by natural disasters, leading to devastating consequences. Communication networks, including television broadcasts, internet connections, and phone services, would also collapse without satellite systems. Satellites relay signals across vast distances, allowing for instant global communication. On a flat Earth, where satellites could not orbit, the ability to communicate worldwide would be severely restricted, plunging humanity back into a less connected era. Astronomy and scientific exploration would suffer greatly as well. Space telescopes like the Hubble, which provide incredible images of distant galaxies and insights into the universe, rely on orbital mechanics to function. In a flat Earth model, such instruments would not be possible, leaving humanity in the dark about the cosmos. The International Space Station, orbiting the Earth and serving as a hub for scientific research, would also be impossible on a flat Earth. The absence of orbital paths would mean no human presence in space, no experiments conducted in zero gravity, and no progress in understanding space travel. Even military defense systems rely on satellites for reconnaissance, missile tracking, and global monitoring. Without satellites, global security strategies would collapse, leaving nations vulnerable and less able to respond to threats. A flat Earth model would completely eliminate the possibility of satellites, erasing some of the most important advancements in modern science, technology, and daily life. The moon provides some of the clearest evidence that Earth is a sphere. During a lunar eclipse, the Earth passes between the sun and the moon, casting a shadow on the moon's surface. This shadow is always round, regardless of the Earth's orientation or position. Only a spherical object consistently produces a circular shadow. If the Earth were flat, the shadow would appear as a line, an oval, or take different shapes depending on the angle of the eclipse. Solar eclipses also contradict the flat Earth model. In a solar eclipse, the moon passes directly between the Earth and the sun, casting a shadow on specific areas of the Earth's surface. The way the shadow moves across Earth, along with its curved path, can only be explained by a spherical Earth rotating on its axis. In a flat Earth system, the sun and moon hovering above a disk could not produce such precise and predictable eclipse patterns. The phases of the moon further reinforce the spherical Earth and moon model. The moon goes through a regular cycle of phases, from new moon to full moon, and back, caused by the angles at which sunlight illuminates its surface as both the Earth and moon move in their orbits. In a flat Earth framework, these phases cannot be explained, as the geometry of light and shadow does not align with what is observed in reality. Lunar eclipses also demonstrate scale and distance. The Earth's shadow can cover the entire moon, showing that the Earth is significantly larger than the moon. On a flat Earth, such a relationship is inconsistent with claims that the moon is close and of equal size to the sun. The predictability of eclipses is another factor. Astronomers can forecast the exact date, time, and location of eclipses centuries in advance using calculations based on a spherical Earth, the moon's orbit, and the sun's position. These predictions consistently match what people observe. A flat Earth model cannot produce the same mathematical accuracy, as its assumptions about celestial movements are inconsistent with the real phenomena. The appearance of the moon itself adds to the evidence. Through telescopes, the moon clearly shows its spherical shape, with craters and shadows curving in ways only possible on a round body. The way light reflects off the moon's surface during its phases further proves it is a sphere illuminated by the sun, not a flat disk or self-lit object. Eclipses, the moon's phases, and the consistent round shadow of Earth provide direct observations that align with a spherical Earth and contradict a flat Earth interpretation. Gravity is one of the strongest demonstrations of Earth's spherical shape. On a round Earth, gravity pulls objects toward the center of the planet, which explains why people on every part of the globe experience down as being toward their feet, even though they are oriented in different directions relative to one another. On a flat Earth, gravity would pull everything toward the center of the disk, causing objects at the edges to lean inward rather than fall straight down, which is not observed. Weight differences across Earth further support its spherical nature. Gravity is not uniform everywhere, because the Earth is not a perfect sphere but an oblate spheroid, slightly flattened at the poles and bulging at the equator. As a result, people weigh slightly less at the equator than at the poles. This difference is measurable and explained by two factors. The equatorial bulge increases the distance from Earth's center, weakening gravity slightly, and the faster rotation of Earth at the equator provides a small outward centrifugal effect, reducing effective weight. Precise measurements from satellites and gravimeters confirm these variations in gravitational strength, mapping the Earth's geoid shape, which shows the planet's uneven distribution of mass. This geoid model is only consistent with a spherical Earth that rotates, not with a flat, stationary plane. Air pressure and atmosphere also connect to gravity. The atmosphere is held close to Earth because gravity pulls air molecules toward the surface. On a flat Earth, without gravity acting toward a central core, the atmosphere would not distribute evenly around the planet. Instead, it would disperse into space, which is not the case. The predictable decrease of air pressure with altitude, measured consistently worldwide, supports the concept of gravity acting on a spherical planet. Tides further demonstrate the interaction of gravity with a spherical Earth. The gravitational pull of the Moon, and to a lesser extent the Sun, creates tides in Earth's oceans. The bulging of water on opposite sides of the Earth occurs because the planet is spherical, and water is free to move around it. On a flat Earth, tides could not occur in this global, predictable pattern, nor could they be calculated with such precision. The behavior of satellites and space travel also relies entirely on gravity acting toward the center of a spherical Earth. Satellites orbit Earth by balancing their forward motion with the pull of gravity toward Earth's core. This would be impossible if gravity did not function as it does on a round planet. Weight differences, gravitational pull, and the distribution of the atmosphere and tides all confirm the spherical nature of Earth, leaving no compatibility with a flat Earth framework. Time zones exist because Earth is a sphere that rotates on its axis once every 24 hours. As the planet rotates, different parts of the globe face the sun while others face away, creating day and night. This rotation means that when it is noon in one location, it is morning, evening, or night in others. A flat Earth would not explain why the sun rises and sets at different times depending on longitude, nor why time zones are necessary. On a flat surface, the sun would have to shine on the entire plane at once, or move in unnatural ways to explain the progression of daylight. The system of 24 standard time zones, each roughly 15 degrees of longitude apart, is directly based on Earth's spherical shape and rotation. For example, when it is sunrise in New York, it is already midday in London and evening in Tokyo. This consistency matches the geometry of a rotating globe and cannot be reconciled with a flat Earth model, where the sun's position would not align with observed local times. Seasons also confirm Earth's spherical nature. Seasons occur because Earth's axis is tilted about 23.5 degrees relative to its orbital plane around the sun. This tilt means that during one part of the year, the northern hemisphere is tilted toward the sun, receiving more direct sunlight and experiencing summer, while the southern hemisphere is tilted away, receiving less sunlight and experiencing winter. 6 months later, the situation reverses, producing opposite seasons between the hemispheres. On a flat Earth, it would be impossible to explain why the northern and southern hemispheres have opposite seasons. A flat Earth model cannot account for the variation in day length, the angle of sunlight, and the changing intensity of heat throughout the year. The tilting of Earth's axis on a spherical body provides a complete explanation, consistent with centuries of observations. The equinoxes and solstices are further evidence of a tilted spherical Earth. During the equinoxes, the sun is positioned directly above the equator, and day and night are nearly equal everywhere on Earth. During the solstices, one hemisphere experiences the longest day and shortest night, while the opposite hemisphere experiences the shortest day and longest night. These events are precisely predictable and measurable, aligning with a globe tilted on its axis. The variation in daylight hours across latitudes also depends on Earth's spherical geometry. Near the poles, the tilt causes extreme conditions, such as the midnight sun in summer, when the sun does not set for weeks, and polar night in winter, when it does not rise for weeks. These phenomena cannot be explained by a flat Earth model, as the sun would have to move in unnatural ways to create such localized effects. Time zones, the cycle of day and night, the progression of seasons, and the predictable solstices and equinoxes all directly result from Earth being a tilted, rotating sphere orbiting the sun. Tectonic activity is one of the most dramatic demonstrations of Earth's spherical and dynamic nature. The planet's crust is divided into plates that float atop the semi-fluid mantle, moving slowly but relentlessly over millions of years. These plates collide, pull apart, and slide past one another, creating mountains, earthquakes, volcanoes, and ocean trenches. On a flat Earth, the mechanics of plate tectonics would not function. The forces that drive these movements depend on the curvature of Earth, the distribution of mass, and the convection currents in the mantle surrounding a spherical core. Mountain ranges like the Himalayas, which formed from the collision of the Indian and Eurasian plates, could not arise in the same way on a flat plane. The immense pressures required to lift vast sections of crust depend on Earth's geometry, gravity toward the center, and the way molten rock circulates beneath the crust. A flat disk would lack the central pull necessary to drive these collisions in the same controlled directions, making the creation of consistent mountain ranges almost impossible. Volcanic activity, too, is closely tied to tectonics and the movement of the Earth's spherical plates. Volcanoes form at convergent boundaries, where one plate is forced beneath another, melting rock into magma that erupts onto the surface. On a flat Earth, subduction zones would not exist in the same way, eliminating the natural process that produces many of the world's volcanoes. Island arcs, volcanic mountain chains, and oceanic ridges would all behave differently or fail to form entirely. Earthquakes are another consequence of plate movement and the elasticity of a spherical crust. Stress accumulates along fault lines, and when it is released, seismic waves ripple outward through the Earth. On a flat disk, the mechanics of these stress accumulations would be inconsistent with observations. The distribution of earthquakes, their intensity, and their propagation through the planet would all be impossible to replicate under a flat Earth model. Ocean trenches, the deepest parts of the seas, are created by the bending of the crust as one plate dies beneath another. The Mariana Trench, nearly 11 kilometers deep, is a direct result of subduction caused by the spherical movement of plates. On a flat Earth, these trenches would be shallower or non-existent, as the necessary forces cannot operate without a central mass exerting gravitational pull. Even volcanic islands in the middle of oceans, such as Hawaii, owe their existence to hotspots and plate motion. The plates move over stationary plumes of magma, creating chains of islands with a clear age progression from older to younger. This pattern relies on the constant, predictable motion of spherical plates across the globe. A flat Earth could not produce such ordered island chains, nor could it explain the progression of geological ages across them. Convection currents in the mantle, which drive plate tectonics, depend on heat from the planet's core rising and falling in a spherical volume. The resulting motion is cyclical and directional, giving rise to consistent patterns of movement. Flatten the planet, and the geometry of these currents changes dramatically. Without a center, the currents would dissipate in chaotic directions, eliminating the orderly motion required for modern geological processes. Tectonic activity also affects climate and ecosystems. Mountains influence rainfall patterns, ocean basins shape currents, and volcanic eruptions can alter atmospheric chemistry for years. All of these phenomena rely on the spherical Earth's dynamics. On a flat disk, the natural interaction between land, ocean, and atmosphere would be entirely different, making familiar landscapes, climates, and ecosystems impossible to replicate. Plate tectonics, earthquakes, volcanoes, mountain ranges, ocean trenches, and the very flow of the mantle all operate in ways that only make sense on a spherical Earth, highlighting the impossibility of reproducing these phenomena on a flat plane. On a spherical Earth, the horizon exists because the planet curves away from the observer. As you look out over the ocean or across a flat plane, distant objects slowly disappear from view bottom first, a phenomenon familiar to anyone watching a ship sail away. This curvature allows for accurate estimation of distances, the way sunsets and sunrises gradually appear and vanish, and even the way tall buildings or mountains are seen from afar. On a flat Earth, this natural visual limitation would not exist. You would be able to see objects thousands of miles away with no obstruction, fundamentally changing how landscapes are experienced and understood. Lighthouses, which are designed to be visible over the curvature of the ocean, would no longer serve their purpose in a flat Earth scenario. Their light would shine much farther than intended, potentially visible across continents. Mariners would not need navigational adjustments based on curvature, but other complications such as uneven terrain and extreme atmospheric distortion would become the primary obstacles to visibility. Astronomical observations also rely on the horizon. The gradual rise and set of celestial bodies, like stars and planets, depend on the Earth's curvature. The North Star appears stationary from the northern hemisphere, while other constellations shift with latitude. On a flat Earth, the entire night sky would be visible at once from any location, eliminating the variation that has allowed humanity to navigate and track seasons for millennia. Optical phenomena, like the green flash at sunset, mirages over deserts, and looming images over water all rely on the bending of light over a curved surface. These phenomena would either disappear or behave inconsistently on a flat plane. Observers might still see distortions due to atmospheric refraction, but the predictable patterns of light and shadow created by curvature would vanish. The horizon also establishes perspective in art, photography, and engineering. Artists use the vanishing point created by the curved horizon to depict depth realistically. Engineers rely on horizon lines when designing structures or mapping large areas. A flat Earth would require rethinking these visual and technical standards, as the cues provided by curvature would no longer exist. Air travel, too, is affected by visibility and horizons. Pilots calculate sightlines for approaches, landings, and takeoffs, and navigational charts account for curvature to ensure safe distances and angles. In a flat Earth scenario, these calculations would have to be entirely redesigned, changing flight patterns and procedures. From the vantage point of a mountain or tall building, the distance to the horizon can be measured using simple geometry, a technique used by surveyors for centuries. Without curvature, such measurements would yield inaccurate results, and long-distance sightlines would extend unnaturally far, allowing impossible views across. Visibility on a flat Earth would not just be extended horizontally, but also distort vertical perception. The disappearance of the horizon would make estimating altitude, distance, and relative scale more difficult, altering perception in ways humans have not adapted to in reality. The interplay between the horizon, curvature, and light fundamentally shapes how humans experience the world visually. On a flat Earth, this entire system collapses, creating an environment where distances are misleading, skies are uniformly visible, and familiar optical phenomena no longer occur as they do on a spherical planet. Air travel relies heavily on the principles of a spherical Earth, including curvature, gravity, and the predictable rotation of the planet. Flight paths are calculated using great circle routes, the shortest distance between 2 points on a sphere. These paths allow planes to save fuel, time, and resources. Flying arcs that appear curved on flat maps, but are actually the most direct routes over the Earth's surface. On a flat Earth, such routes would be unnecessary or nonsensical. A plane traveling from New York to Tokyo would not need to arc over the Arctic. Instead, pilots would attempt a straight line, encountering vastly different distances and logistical challenges that do not match reality. Navigation systems in aviation rely on GPS satellites, which orbit the Earth in precise paths. These systems provide accurate latitude, longitude, altitude, and timing data, allowing pilots to follow safe flight corridors. On a flat Earth, satellite orbits would be impossible, eliminating GPS functionality. Pilots would be forced to rely on outdated methods such as visual navigation, radio beacons, and dead reckoning, which are far less reliable and increase the risk of navigational errors. Flight instruments, such as the altimeter, airspeed indicator, and artificial horizon, are calibrated based on spherical Earth assumptions and gravitational forces toward the center of the planet. The altimeter, for example, measures atmospheric pressure, which decreases predictably with altitude due to gravity. On a flat Earth, air pressure would not behave in the same way, making altitude readings inaccurate and potentially hazardous. Long-haul flights, particularly over oceans and polar regions, depend on the Earth's curvature to plan fuel stops and emergency diversion airports. Great circle routes often pass over regions where airports are sparse, requiring careful contingency planning. Without a globe, flight planning would miscalculate distances and timing, increasing risk and uncertainty for both crew and passengers. The concept of time zones is also crucial for aviation. Scheduling departures and arrivals requires precise coordination across multiple time zones created by Earth's rotation. In a flat Earth scenario with no rotation-based time zones, the synchronization of flights across continents would be confusing. Airlines could not rely on standard local times, leading to scheduling chaos and operational inefficiency. Weather prediction plays an integral role in aviation safety. Meteorological satellites provide data on storms, jet streams, and wind patterns, all influenced by Earth's spherical shape and rotation. Pilots adjust flight paths to avoid turbulence and storms based on these data. On a flat Earth, without proper satellite coverage or atmospheric modeling aligned to a spherical planet, these predictions would be unreliable, increasing the risk of encountering severe weather unexpectedly. Even airport design and navigation aids are based on a round-Earth model. Runways are aligned considering prevailing winds, magnetic declination, and curvature over long distances. Air traffic control relies on radar systems calibrated for spherical geometry, ensuring planes maintain proper separation and altitude. Flatten the planet, and all these systems would require recalibration, with unpredictable consequences for safety and efficiency. Global aviation logistics, from cargo shipping to passenger travel, are intricately tied to Earth's spherical geometry. Long-haul international flights, polar crossings, and circumnavigation depend on rotation, gravity, and the curvature that dictates distances and navigation. Without these elements, air travel would become unpredictable, inefficient, and far more dangerous than anything currently experienced. Maps are human attempts to represent the curved surface of Earth on flat paper, which always introduces some form of distortion. On a spherical Earth, any two-dimensional map must compromise in areas like shape, distance, or area. The Mercator projection, for example, preserves angles for navigation but drastically enlarges regions near the poles, making Greenland appear bigger than Africa, even though it is much smaller. On a flat Earth, these distortions would vanish only if the world were actually flat. But in reality, every map projection we use accurately reflects the curvature and geometry of a round planet. Flat Earth maps often attempt to depict the world as a disk, with the North Pole at the center and continents stretching outward toward the edges. However, these maps fail to reproduce real-world distances and relative sizes accurately. Traveling from South America to Australia, for instance, would show inconsistencies in flight distances that do not match observed flight times and fuel requirements. Geographic coordinates, latitude and longitude, and global positioning are based on a spherical Earth, making flat Earth representations mathematically incompatible with navigation. The scale of continents and oceans is also affected by curvature. On a globe, distances between continents follow curved paths over the surface, which is why great circle routes are shorter than straight lines on a flat map. Flat Earth models ignore these arcs, resulting in predicted distances that are either too long or too short compared to reality. For example, a supposed direct flight across the Pacific would require completely different fuel calculations. Yet every commercial airline adheres to spherical Earth assumptions and arrives on schedule, proving the globe model. Political and cultural mapping also depends on spherical geometry. Time zones, climate zones, and hemispheric divisions are all created using a round Earth framework. Flat Earth representations distort these zones, making climate predictions, daylight cycles, and even cultural timekeeping illogical. Farmers, scientists, and governments rely on these divisions for agriculture, research, and planning, which would all fail under a flat disk model. Historical cartography relied on observations of the horizon, celestial navigation, and circumnavigation to understand Earth's curvature. Explorers like Magellan and Columbus used spherical Earth assumptions to plan routes, which led to successful voyages around the globe. Attempting the same expeditions on a flat Earth map would have led to catastrophic errors, miscalculations, and impossible journeys. Even modern mapping systems, like Google Maps, rely on spherical coordinates and satellite imagery. GPS systems calculate positions using signals from satellites orbiting around Earth, triangulating locations with extreme precision. In a flat Earth scenario, these calculations would be impossible, and digital maps would no longer correspond with reality, leaving navigation unreliable and chaotic. Geographic features such as mountain ranges, rivers, and ocean currents follow patterns dictated by the planet's curvature and rotation. A flat Earth map would distort these features, misrepresenting water flow, mountain orientation, and climate effects. The interconnectedness of geography, weather, and human activity is inherently linked to the globe's spherical shape. Distortions in maps, navigation, distances, and geographic understanding all point back to the reality of a spherical Earth. Flat Earth representations fail to align with observed measurements, satellite data, and navigational accuracy, proving the necessity of considering curvature in every aspect of mapping and geography. The night sky provides some of the most compelling evidence for a spherical Earth. Constellations appear differently depending on your latitude. For example, the Big Dipper is visible year-round in the Northern Hemisphere, but cannot be seen at all from most locations in the Southern Hemisphere. Conversely, the Southern Cross is only visible in the Southern Hemisphere. On a flat Earth, every constellation would be visible from every point on the disk at the same time, which is not what we observe. The movement of stars across the sky also depends on Earth's rotation and curvature. Stars rise in the east and set in the west, tracing arcs that vary depending on latitude. Near the poles, stars move in tight circles around the celestial poles, while near the equator, stars appear to rise and set nearly vertically. This variation can be measured precisely and predicts the positions of stars at any time. A flat Earth cannot explain these changes in star movement. Eclipses, both lunar and solar, depend on the precise alignment of the Sun, Moon, and Earth in a three-dimensional. The predictability of these eclipses, from anywhere on the planet, relies on the spherical geometry of the Earth. Ancient civilizations like the Babylonians and Greeks could forecast eclipses using this knowledge, which would not work on a flat disk. The apparent size and position of celestial bodies also change with latitude. The North Star, Polaris, appears higher in the sky as you move northward and eventually disappears as you move south. This gradient is only possible because of the spherical nature of Earth. On a flat plane, Polaris would either be visible everywhere or not at all, contradicting centuries of observational astronomy. The rotation of the Earth produces the phenomenon of circumpolar stars, those that never set and circle the celestial pole. Observers in the northern hemisphere see different circumpolar stars than those in the southern hemisphere. This is consistent with a round Earth rotating on its axis. Flat Earth models cannot reproduce this phenomenon accurately. Planetary motion also aligns with a spherical Earth. Observations of Mercury, Venus, Mars, Jupiter, and Saturn demonstrate consistent retrograde motions and positions relative to Earth. Calculations for these motions are based on heliocentric models with a spherical Earth and orbiting planets. A flat Earth cannot account for these patterns without resorting to convoluted explanations. Astronomers use parallax, the apparent shift of nearby stars against distant ones as Earth moves in its orbit, to calculate distances to stars. Parallax measurements are consistent with a spherical Earth revolving around the Sun. On a flat Earth, the geometry of these measurements would not align with observed shifts, making astronomical distance calculations impossible. Even modern telescopes, both ground-based and orbital, rely on the spherical Earth to track objects accurately. Satellites and space telescopes must account for Earth's curvature when aiming at distant stars, planets, or galaxies. This precise targeting would fail on a flat Earth, rendering modern observational astronomy impractical. The patterns of constellations, the movement of stars, eclipses, planetary motions, circumpolar stars, and parallax all directly support the spherical Earth model. Observations from any latitude consistently align with this reality, leaving flat Earth explanations unable to replicate the celestial mechanics observed over centuries. Earth's spherical shape and axial tilt are fundamental to the creation of weather systems and climate zones. The rotation of the planet generates the Coriolis effect, which influences wind patterns, ocean currents, and the formation of cyclones and anticyclones. On a flat Earth, the Coriolis effect would not exist as we observe it, meaning hurricanes and large-scale wind patterns would behave unpredictably or fail to form in the same way. Climate zones, tropical, temperate, and polar, are created by the angle at which sunlight strikes the Earth. Near the equator, sunlight hits directly, producing heat and tropical climates, while at the poles, sunlight strikes at a shallow angle, generating frigid conditions. A flat Earth model cannot explain the gradual changes in temperature from equator to poles, or the distinct characteristics of each climate zone, as sunlight would either illuminate the entire disk evenly or create inconsistent heating. Jet streams, which are fast-flowing air currents in the upper atmosphere, are influenced by Earth's rotation and the temperature differences between equatorial and polar regions. These streams guide storms and influence weather patterns across continents. Without a spherical Earth, the formation and behavior of jet streams would not align with observed meteorological phenomena. Ocean currents, such as the Gulf Stream and the Antarctic Circumpolar Current, rely on the combination of Earth's rotation, wind patterns, and the distribution of land masses across a sphere. These currents regulate climate by redistributing heat around the planet, creating milder coastal climates and influencing rainfall patterns. On a flat Earth, ocean currents would behave chaotically, failing to support the observed stability of climate zones. The distribution of rainfall is also tied to the globe's shape. The Hadley, Fell, and polar cells move air in predictable cycles, producing deserts near 30 degrees latitude, rainforests near the equator, and polar dry zones. These patterns are consistent globally and can be modeled accurately because Earth is spherical. Flattening the planet would disrupt this balance, making predictable rainfall patterns impossible. Seasonal storms and phenomena, such as monsoons and tornadoes, are shaped by Earth's curvature and rotation. Monsoons, for example, result from the differential heating of land and sea, which is modulated by the tilt and spherical distribution of sunlight. Tornado formation is influenced by the interaction of warm and cold air masses guided by global wind patterns. A flat Earth cannot replicate these seasonal and regional weather phenomena accurately. Altitude and latitude together influence temperature and weather in complex ways. High mountains near the equator, like the Andes, have snow-capped peaks despite being in tropical regions, because of elevation and the way Earth's curvature affects atmospheric pressure and temperature distribution. On a flat Earth, such variations would be far less predictable or inconsistent. The interplay between Earth's rotation, tilt, curvature, and energy from the sun creates reliable climate zones, seasonal shifts, and extreme weather systems. The global distribution of deserts, forests, polar ice, and temperate zones all align with the geometry of a spherical Earth, forming patterns that flat Earth models cannot replicate. Earth's rotation is central to understanding day and night, weather patterns, ocean currents, and even the way objects fall. Spinning on its axis once every 24 hours, the planet creates a centrifugal force that slightly counteracts gravity at the equator, causing Earth to bulge slightly in that region. This oblateness affects sea level, satellite orbits, and even the length of a day. On a flat Earth, rotation in this manner is physically impossible. A disk spinning to mimic a day-night cycle would produce extreme centrifugal forces, flinging everything on its surface outward toward the edges. The Coriolis effect, a direct result of rotation, governs the direction of moving air and water. In the northern hemisphere, hurricanes spin counterclockwise, and in the southern hemisphere, clockwise. Ocean currents, trade winds, and even the path of long-range projectiles are influenced by this rotation-induced effect. Without a rotating sphere, these predictable patterns disappear, and observed behavior of wind and water could not be explained. Rotation also affects the apparent motion of celestial bodies. The sun, moon, and stars appear to rise and set because of the Earth's rotation. Foucault's pendulum, which demonstrates the gradual change in the plane of oscillation over time, directly measures Earth's rotation. On a flat Earth, a stationary or slowly circling sun would fail to reproduce these observed effects, making astronomical observations inconsistent. Satellites and spacecraft navigation rely on precise calculations of Earth's rotation. Orbits must match the planet's angular velocity to maintain geostationary positions or complete circumnavigations. On a flat rotating disk, such orbits would be impossible, as centrifugal forces would interfere with satellite stability, preventing GPS, weather observation, and communications from functioning correctly. The rotational bulge of Earth also affects gravity measurements. Geophysicists detect slightly weaker gravity at the equator than at the poles, a direct result of centrifugal force from rotation. This subtle difference is measurable with gravimeters and aligns perfectly with predictions based on a rotating sphere. A flat Earth spinning in any fashion would fail to produce these exact variations. Rotation interacts with tidal forces too. While the moon primarily drives tides, Earth's spin causes tidal bulges to be slightly ahead of the moon, creating tidal friction that gradually slows Earth's rotation. This feedback loop, observable over geological timescales, is impossible to replicate on a flat disk, where tidal mechanics would differ dramatically or fail entirely. Coriolis-influenced weather, centrifugal forces, satellite mechanics, gravitational variation, and tidal interactions all depend on the physics of a rotating sphere. These phenomena are measurable, consistent, and observable worldwide, highlighting the impossibility of reproducing them on a flat, non-rotating surface. Earth's core and internal geology are essential to understanding its magnetic field, heat flow, and tectonic activity. The planet has a layered structure with a solid inner core, a molten outer core, a viscous mantle, and a rigid crust. The rotation of the molten outer core generates the geomagnetic field, which shields the planet from harmful solar radiation. On a flat Earth, this mechanism would not exist. A disk cannot support a central molten core in the same way, meaning there would be no natural magnetic field to protect life or influence compasses. Volcanic activity also depends on Earth's internal heat and spherical structure. Magma rises through weak points in the crust, forming volcanoes, mid-ocean ridges, and hotspots. These processes rely on the pressure and convection currents within a spherical mantle. On a flat disk, mantle convection would be disrupted, leading to unpredictable or entirely absent volcanic activity. Earth's core also drives geothermal gradients, with heat radiating outward from the inner core. This energy warms the mantle, powers plate tectonics, and contributes to the recycling of crustal material. Without a spherical geometry and central core, this flow of energy would be impossible to organize systematically, disrupting the formation of mountains, ocean trenches, and continental drift. Earth's layers are also responsible for the propagation of seismic waves. During earthquakes, primary, secondary, and surface waves move through the planet, revealing the internal structure. Seismology has confirmed a dense core and layered mantle consistent with a spherical Earth. On a flat Earth, these wave behaviors could not match observations, and earthquake predictions and measurements would fail to correspond with reality. Mineral formation and rock cycles are tied to internal geology. The heat and pressure generated deep within the Earth create metamorphic rocks, while the melting and cooling of magma produce igneous formations. Sedimentary layers accumulate over time, influenced by gravity and the movement of tectonic plates. A flat Earth would lack the same internal pressures and convection patterns, altering the very foundation of geology as we know it. Earth's magnetic field also interacts with the atmosphere, forming auroras near the poles as charged particles are funneled along magnetic lines of force. This phenomenon depends on a central, rotating core and spherical geometry. Without it, auroras would not exist, and solar radiation would strip away parts of the atmosphere, especially at the edges of a flat disk. Heat from the core drives mantle plumes, creating volcanic island chains like Hawaii. The age progression of these islands, from oldest to youngest, depends on the motion of spherical plates over stationary hotspots. On a flat Earth, this progression would not exist in the same ordered pattern. The internal structure of the planet, from core to crust, dictates gravity, magnetic protection, tectonics, volcanism, and the rock cycle. Without a spherical Earth and central core, all of these fundamental geological processes would behave differently or fail entirely. The development of human civilization is intricately linked to a spherical Earth. Geography, climate, and natural resources all follow patterns dictated by the planet's curvature, rotation, and axial tilt. Agricultural regions, river valleys, and fertile plains are distributed in ways that make sense only on a globe. Ancient civilizations like Mesopotamia, the Nile Valley, and the Indus Valley thrived where predictable river flooding and seasonal cycles supported crop growth. On a flat Earth, these patterns would be fundamentally different, disrupting the development of societies dependent on reliable environmental conditions. Navigation and exploration have shaped human history, relying on the roundness of the Earth. Early explorers used celestial navigation, observing stars and the horizon to determine latitude and longitude. The successful circumnavigation by Ferdinand, Magellan's expedition in 1519 to 1522 depended on the understanding that Earth is a sphere. On a flat Earth, these voyages would be impossible, distances miscalculated, and trade routes disrupted, fundamentally altering the course of global history. Timekeeping, calendars, and astronomy also depend on a spherical planet. The Earth's rotation and orbit around the Sun create days, years, and seasons. Civilizations from the Egyptians to the Mayans built advanced calendars by observing these cycles, predicting eclipses, solstices, and equinoxes. A flat Earth would produce radically different solar patterns, making historical astronomy and the development of accurate calendars impossible. Trade and cultural exchange relied on long-distance travel that assumed a spherical world. Sea routes, overland caravans, and early air navigation all used great circle approximations for efficient travel. Maps and navigation instruments reflect these calculations. Flat Earth models would disrupt the logistics of historical trade networks, potentially preventing the spread of ideas, technology, and cultural practices. The rise of empires also relied on the predictability of Earth's surface. Empires like Rome, Persia, and China expanded along landforms, rivers, and coastlines that are consistent with the globe. The curvature of Earth influenced the placement of cities, fortifications, and supply routes, shaping political and military strategies. A flat Earth would alter these dynamics, creating inconsistencies in strategic planning. Exploration of polar regions further demonstrates humanity's understanding of Earth's sphericity. Expeditions to the North and South Poles revealed converging lines of longitude and consistent celestial observations. These findings validated the spherical Earth and informed navigation, cartography, and scientific research. On a flat Earth, these polar observations would be impossible to reconcile with reality. Satellite imagery, modern aviation, and global communication systems have extended human civilization across the planet. GPS, weather monitoring, and telecommunication satellites orbit the spherical Earth, providing services that connect continents and nations. On a flat Earth, these technologies would be unworkable, limiting the capacity for global coordination, trade, and scientific progress. The distribution of human populations, cities, and infrastructure follows patterns shaped by climate zones, ocean currents, and resource availability, all dictated by Earth's round shape and rotation. Flattening the planet would disrupt these patterns, making many historical developments and modern civilizations appear impossible or inexplicable. From agriculture to exploration, empire building to modern technology, human civilization is deeply intertwined with the geometry and dynamics of a spherical Earth. The way societies evolved, expanded, and connected relies on predictable environmental, navigational, and astronomical phenomena that only a globe can provide. Observing Earth from a cosmic perspective offers undeniable evidence of its spherical nature. From space, astronauts see a round planet suspended in the vast darkness of the universe, illuminated by the sun. The curvature is visible in photographs taken from the International Space Station and in images captured by satellites orbiting Earth. On a flat Earth, these views would appear fundamentally different, with edges visible and no gradual curvature. Yet every observation aligns with a globe. The way Earth interacts with other celestial bodies further reinforces its roundness. Lunar eclipses occur when Earth passes between the Sun and Moon, casting a circular shadow on the lunar surface. This round shadow is consistent regardless of where on Earth the eclipse is observed, something that flat Earth models cannot replicate accurately. Ancient astronomers, including Aristotle around 330 BCE, noted the consistent round shadow during eclipses as evidence for a spherical planet. Earth's orbit around the Sun and its axial tilt shape the cosmic perspective of seasons and sunlight angles. Observers on different continents see the Sun at different heights in the sky at the same moment, creating variations in daylight and temperature that flat Earth scenarios cannot produce. The tilt of 23.5 degrees also explains seasonal changes, solstices, and equinoxes consistently across hemispheres. Planetary transits, such as those of Mercury and Venus across the Sun, rely on the geometry of a spherical Earth to predict timing and visibility. Observers around the world see slightly different transit paths depending on their latitude, which aligns with the curvature of Earth. Flat Earth models fail to produce the same observational data or predict events accurately. The cosmic perspective also includes the apparent movement of stars and planets. Constellations rotate around the celestial poles, and their visibility changes with latitude. Circumpolar stars never set near the poles, while equatorial observers see stars rise and set nearly vertically. Space-based observations confirm these patterns and rely on spherical geometry to calculate positions and predict movement. Satellites and space missions provide additional cosmic verification. GPS satellites orbit at specific altitudes and trajectories calculated based on Earth's curvature. Weather satellites monitor storms globally, while space telescopes like Hubble rely on precise alignment with Earth's spherical orbit to target distant galaxies. A flat Earth could not support the orbital mechanics required for these operations. Observing Earth from afar also highlights the atmosphere's layered structure. The way light scatters, producing sunsets, sunrises, and blue skies, is influenced by curvature. The gradual thinning of the atmosphere at higher altitudes and the visible limb of Earth from space provide direct visual evidence of a round planet. On a flat Earth, these effects would appear dramatically different, inconsistent with what astronauts and satellites record. Even gravity, when viewed from space, behaves as if all mass is concentrated toward the planet's center, producing a near-perfect sphere. The behavior of oceans, tides, and the distribution of continents aligns with gravitational pull toward a central point, which flat disk models cannot replicate. The cosmic perspective from eclipses to planetary transits, star movements, satellite operations, and orbital mechanics consistently confirms that Earth is a globe. Observations from above, combined with centuries of astronomical study, make the spherical nature of our planet evident across time and space. Modern communication systems rely on the spherical shape of Earth for satellite-based technologies. Geostationary satellites orbit approximately 35,786 kilometers above the equator, matching Earth's rotation so they remain fixed over a specific point. This allows continuous communication signals for television, internet, and phone networks. On a flat Earth, geostationary orbits are impossible, as there is no curvature to match the rotational mechanics needed for satellites to hover in a fixed position. GPS systems are essential for navigation, emergency response, and logistics. These satellites calculate positions using precise measurements of time and distance, assuming Earth is a globe. Receivers triangulate signals from multiple satellites to determine latitude, longitude, and altitude. A flat Earth could not support this triangulation method, rendering GPS unreliable or non-functional. International telecommunications also rely on satellites to transmit signals across vast distances. Fiber optic cables alone cannot cover remote regions, oceans, or polar areas without signal latency or interruption. Satellite relay depends on predictable orbital paths above a spherical Earth, ensuring coverage continuity. Flat Earth models cannot explain how signals could maintain such consistent timing and accuracy over long distances. Weather forecasting and climate monitoring utilize satellites to observe cloud formations, storms, and atmospheric conditions globally. These observations depend on the curvature of Earth for accurate satellite imaging, enabling meteorologists to track hurricanes, typhoons, and extreme weather events. Flat Earth perspectives would misalign imaging, making reliable weather prediction impossible. Even space-based radio communication, such as deep space network connections to spacecraft exploring other planets, relies on Earth's spherical geometry. Ground antennas are positioned based on curvature, allowing continuous contact as Earth rotates. Flat Earth models cannot account for these adjustments, which are essential for uninterrupted communication with distant probes. Television broadcasting from satellites, including high-definition and live signals, depends on line-of-sight transmission and geostationary positioning. Satellites maintain altitude and positioning through calculations based on Earth's mass, gravity, and rotation, all dependent on a globe. On a flat Earth, these mechanics would fail, disrupting signal coverage and continuity. The distribution of cell towers and radio networks also interacts with Earth's curvature. Radio waves follow slightly curved paths, and long-distance communication over the horizon is possible due to atmospheric refraction and Earth's shape. Flatten the planet, and these distances and propagation patterns would not match observed coverage, particularly for high-frequency signals. Global internet connectivity, including satellite constellations like Starlink, depends on precise orbital mechanics and Earth's curvature. Signals from these satellites are carefully calculated to avoid interference, maintain speed, and reach remote regions. Flat Earth scenarios would make this technological feat impossible to replicate with the same efficiency and reliability. Emergency alert systems, aviation communication, and maritime coordination all rely on satellite links that assume Earth is a sphere. From sending distress signals in the open ocean to coordinating air traffic across continents, the accuracy and dependability of these systems demonstrate the spherical geometry underlying modern ocean networks. Observing the efficiency, reliability, and global reach of communication systems from GPS to satellites, internet networks to radio transmission, highlights the practical dependence on a spherical Earth, showing how technology functions consistently with the planet's curvature and orbital mechanics. Space exploration provides some of the most direct and compelling evidence for a spherical Earth. Since the launch of Sputnik in 1957, humans have sent satellites, probes, and crewed missions into orbit, all of which rely on calculations based on a globe. Spacecraft trajectories, orbital mechanics, and docking procedures assume a round planet, and every mission from Apollo lunar landings to the International Space Station confirms the accuracy of these models. Astronauts aboard the International Space Station, ISS, experience a continuous view of Earth's curvature. High-resolution photographs and live video streams reveal the planet as a round, rotating sphere, complete with weather patterns, cloud formations, and the limb visible against the darkness of space. On a flat Earth, this curvature and consistent observation would be impossible to reproduce. Orbital satellites also demonstrate the necessity of a spherical Earth. Geostationary satellites maintain fixed positions above the equator to provide communications, weather monitoring, and global navigation. Low Earth orbit satellites circle the globe, capturing imagery and data across all latitudes. These orbits and the ability to calculate satellite positions precisely depend on Earth's round geometry. Lunar missions provide indirect confirmation of Earth's shape. Photographs of Earth from the Moon, starting with Apollo 8 in 1968, show a full, round planet suspended in space. The phases of Earth observed from the lunar surface align with the way the Moon is seen from Earth, demonstrating the interplay of two spherical celestial bodies in orbit. Mars rovers and interplanetary probes rely on Earth-based calculations for launch and navigation. Trajectories to other planets are plotted using the planet's mass, gravity, and curvature. These calculations would be impossible on a flat disk, and the success of interplanetary missions validates spherical Earth models. Earth observation satellites provide precise mapping, weather forecasting, and environmental monitoring. Satellite imagery tracks deforestation, ice cap melting, and ocean currents with accuracy that aligns perfectly with a globe. On a flat Earth, the consistent coverage of all latitudes and hemispheres would be unachievable. International space programs, including NASA, ESA, Roscosmos, CNSA, and ISRO, collaborate on orbital stations, interplanetary missions, and Earth monitoring systems. Their coordination requires agreement on Earth's curvature and rotation to synchronize launches, docking, and orbital insertion. Flat Earth assumptions would make such collaboration mathematically and practically impossible. The Hubble Space Telescope and other space-based observatories orbit Earth to avoid atmospheric interference. Their stable orbits and ability to image distant galaxies depend on precise knowledge of Earth's gravitational pull, which is shaped by a spherical planet. Any deviation from this geometry would disrupt observations and orbital stability. Space-based GPS, satellite communication, and weather monitoring rely on the predictability of orbital mechanics around Earth. Launch windows, satellite spacing, and coverage maps all operate according to spherical calculations, enabling the global technological systems that humans depend on today. The cumulative evidence from space exploration, including orbital trajectories, satellite imagery, astronaut observations, lunar photography, interplanetary navigation, and global monitoring consistently confirms that Earth is a sphere. Each mission and observation aligns with theoretical predictions based on a round planet, making alternative flat Earth explanations impossible to reconcile with the data. The polar regions provide striking evidence of Earth's spherical nature through unique geographic, climatic, and astronomical phenomena. The Arctic and Antarctic are defined by the convergence of longitudinal lines at the poles, creating circular patterns of ice, land, and ocean. On a flat Earth, these regions would not exist in the same way. There would be no converging meridians, no polar circumpolar currents, and no defined ice caps as observed today. The behavior of sunlight in polar regions demonstrates Earth's tilt and curvature. During summer months, the poles experience continuous daylight for weeks, while in winter, they undergo extended periods of darkness. This phenomenon, known as the midnight sun and polar night, occurs because the axial tilt of 23.5 degrees allows the sun to circle above the horizon or remain below it. Flat Earth models cannot replicate this consistent seasonal behavior. Ice sheets and glaciers in the polar regions grow and shrink, based on global climatic cycles influenced by Earth's orbit and tilt. The Antarctic ice sheet, for example, holds roughly 60% of the planet's fresh water and affects global sea levels. These patterns of accumulation and melt are influenced by spherical geometry, with thickness variations and flow directions aligning with gravity toward a central mass. On a flat Earth, such consistent glacial behavior would be unexplainable. Polar exploration offers further evidence. Expeditions to the North and South Poles track latitude and longitude precisely, navigating over converging meridians. Early explorers like Roald Amundsen and Robert Falcon Scott measured distances and celestial positions, confirming spherical geometry. Their routes and discoveries would be impossible to reproduce on a flat disk without massive discrepancies. The polar vortex and atmospheric circulation are directly influenced by Earth's rotation and curvature. Air currents around the poles form stable, rotating patterns that impact weather globally. These patterns interact with the jet streams and influence temperature distribution in mid-latitudes. On a flat Earth, such polar wind systems would behave unpredictably, failing to produce observed global climatic patterns. Auroras, the northern and southern lights, occur near the poles due to charged particles interacting with Earth's magnetic field. The location, shape, and intensity of auroras are consistent with a magnetic field generated by a rotating, molten core at the center of a spherical Earth. On a flat disk without a central core or proper geomagnetic configuration, auroras would not exist in the same predictable way. Sea ice distribution and ocean currents around the poles are shaped by spherical geometry. The Antarctic circumpolar current flows uninterrupted around the southern hemisphere, connecting oceans and regulating global climate. The Arctic Ocean, constrained by surrounding continents, exhibits a different circulation pattern. These ocean behaviors depend on Earth's curvature and rotation. A flat Earth would produce entirely different, unobserved patterns. Polar star observations provide additional evidence of sphericity. In the northern hemisphere, stars rotate around Polaris, the North Star, while in the southern hemisphere, stars rotate around Sigma Octantis and other southern circumpolar stars. The visibility of these constellations from specific latitudes aligns with a round Earth. On a flat Earth, all stars would be visible simultaneously from everywhere, contradicting centuries of astronomical observations. Ice cores drilled in Greenland and Antarctica reveal climatic history, atmospheric composition, and even volcanic events over hundreds of thousands of years. The accumulation and layering of ice, influenced by gravity, pressure, and snowfall patterns across the globe, are consistent with spherical geometry. On a flat disk, ice deposition would not create the same continuous, predictable record. From sunlight patterns to magnetic phenomena, atmospheric circulation to ocean currents, polar regions consistently demonstrate the effects of a spherical Earth. Exploration, scientific measurements, and natural phenomena all align with a globe, making the polar regions one of the clearest pieces of evidence for Earth's round shape. Artificial satellites are integral to modern communication, navigation, weather monitoring, and scientific observation. On a spherical Earth, satellites orbit at precise altitudes and velocities, maintaining geostationary or low Earth orbits to provide continuous coverage. The concept of replacing these satellites with alternative systems, such as high-altitude balloons, ground-based towers, or drones, exposes the limitations of a flat Earth scenario. Geostationary satellites rely on orbiting directly above the equator at 35,786 kilometers, matching Earth's rotation to appear stationary relative to the surface. This allows uninterrupted television broadcasting, internet services, and satellite phones. Replacing them with stationary platforms on a flat Earth would require impossible heights and structural integrity, as no tower or balloon could remain fixed without being affected by wind, gravity, and atmospheric conditions. Low Earth orbit satellites, which operate between 160 and 2,000 kilometers, provide high-resolution imaging, GPS, and real-time Earth observation. These satellites travel at thousands of kilometers per hour to maintain orbit. A flat Earth alternative would necessitate an entirely different physics model for maintaining stable altitude and position, which fails to account for continuous coverage or accurate positioning across the globe. Navigation systems like GPS depend on a constellation of satellites to triangulate positions anywhere on Earth. Signals from multiple satellites are received simultaneously to determine precise coordinates. Flat Earth replacements, such as stationary ground stations or high-altitude balloons, could not provide the same global coverage or precision, leaving vast areas without reliable navigation. Weather monitoring and climate observation rely heavily on satellites for detecting storms, tracking hurricanes, and measuring global temperatures. The orbital perspective allows meteorologists to observe phenomena across hemispheres simultaneously. High-altitude alternatives on a flat Earth would face limited range, atmospheric interference, and no ability to track global patterns effectively. Earth observation for environmental monitoring, deforestation, ice sheet melting, ocean currents, and urban development requires consistent satellite imaging. Geospatial data collected from satellites are used in disaster management, urban planning, and ecological studies. Flat Earth substitutes would fail to provide uniform data coverage and the continuity required for accurate analysis. Telecommunications satellites provide international phone calls, television broadcasts, and internet connectivity. Geostationary positioning ensures minimal signal delay. On a flat Earth, replacing these satellites with other systems would introduce massive latency, signal degradation, and coverage gaps, disrupting global communication. Military and scientific applications also rely on orbital satellites. Reconnaissance, missile warning, and deep space observation require predictable orbits around a spherical Earth. Flat Earth alternatives would be incapable of maintaining consistent lines of sight, coverage areas, or accurate timing for sensitive operations. Even space-based internet constellations such as Starlink depend on a network of low Earth orbit satellites to provide high-speed internet globally. These constellations function as a mesh, continuously moving in sync with Earth's rotation. High-altitude flat Earth alternatives would fail to replicate this dynamic network, leaving large areas underserved. The feasibility, precision, and global functionality of artificial satellites cannot be duplicated by any terrestrial or flat Earth-based system. From navigation and weather forecasting to communication and scientific observation, satellites exploit the spherical geometry of Earth and orbital mechanics to provide services that no replacement on a flat disk could reliably reproduce. Timekeeping and calendars are fundamentally linked to the spherical shape and rotation of Earth. The 24-hour day is based on a complete rotation of the planet on its axis, while the 365.25-day year corresponds to Earth's orbit around the Sun. Ancient civilizations, from the Egyptians to the Mayans, carefully observed celestial movements, noting how the sun, moon, and stars shifted relative to the horizon. These observations allowed the creation of accurate calendars, solstices, equinoxes, and timekeeping systems that remain remarkably consistent today. The division of time into hours, minutes, and seconds relies on predictable rotation and angular movement. Mechanical clocks, sundials, and even atomic clocks depend on the regularity of Earth's rotation. On a flat Earth, the circular motion of the sun proposed in some models would fail to create consistent day-night cycles, making uniform timekeeping impossible. Time zones are another consequence of a spherical planet. As Earth rotates, different longitudes experience sunlight at different times, creating the need for standardized local time. Countries adjust their clocks to match longitudinal position, ensuring coordination for commerce, travel, and communication. Flat Earth models cannot reconcile these observed differences. If the sun hovered over the disk, simultaneous daylight across vast distances would eliminate the logic of time zones. Seasonal variations also arise from Earth's axial tilt and orbit around the sun. Solstices, equinoxes, and the changing angle of sunlight throughout the year regulate agricultural cycles, animal migrations, and cultural festivals. The tilt ensures longer days in summer and shorter days in winter for each hemisphere. Flat Earth theories fail to produce these consistent seasonal changes across different latitudes. Historical records, such as the Antikythera mechanism, demonstrate ancient understanding of astronomical cycles, eclipses, and planetary motion. These sophisticated devices could only function with the knowledge of a spherical Earth, predicting celestial events with accuracy. A flat disk model could not account for these calculations. Calendars also rely on lunar cycles and solar positions. Months, weeks, and leap years are designed to reconcile the differences between the moon's phases and the solar year. Observed lunar eclipses, the progression of constellations, and the shifting sun in the sky all match predictions based on Earth's round orbit. On a flat Earth, these correlations would break down, producing observable discrepancies. Longitude measurement and maritime navigation historically depended on accurate timekeeping. Ships use chronometers to determine their east-west position by comparing local time with a reference meridian. This method relies on the Earth's rotation and a spherical geometry. A flat Earth would render such calculations inaccurate and inconsistent. Even modern timekeeping, from GPS satellites to global clocks, assumes a round Earth. Satellite orbits are synchronized with Earth's rotation to provide precise timing signals for financial markets, navigation, and scientific experiments. A flat Earth would disrupt these calculations, making global time synchronization unreliable. Observing solar and lunar eclipses across different continents demonstrates the dependence of timekeeping on Earth's geometry. The timing, duration, and shadow paths align perfectly with a rotating sphere. Flat Earth scenarios fail to explain why eclipses are visible at specific locations and times but not others. From ancient calendars to atomic clocks, from time zones to global navigation, the measurement of time and structuring of calendars rely on Earth's spherical shape and rotation. The consistency and predictability of day-night cycles, seasons, and celestial observations are directly tied to the geometry and dynamics of a round planet. If the Earth were flat, much of modern science and technology would collapse, because they are built on the understanding of a spherical planet. Physics, astronomy, geology, and many other fields rely on the globe model to explain natural phenomena accurately. For example, Newton's law of gravitation assumes a nearly spherical Earth with mass pulling toward its center. Without this, calculations of motion and force would fail. Einstein's theories of relativity, which explain gravity, light, and space-time, also depend on a spherical orbiting Earth. Technologies such as GPS, satellite communication, and weather prediction rely on orbital mechanics and the curvature of Earth. These would not function as they do if Earth were flat, since the mathematics behind them requires a globe. Airplanes and ships use great circle navigation routes, which only make sense on a sphere. Engineering, construction, and even basic surveying are built on geodesy, the science of Earth's shape and size, which would collapse under a flat Earth. Medical imaging technologies, such as MRI and CT scans, rely on principles of physics that were tested and proven using a spherical Earth in a heliocentric solar system. Modern chemistry and geology also assume planetary formation and internal structure consistent with a globe. Even space exploration, from rocket launches to satellite trajectories, is impossible without spherical Earth models. Entire branches of science, from climatology to astrophysics, would break apart, as their predictions, observations, and equations depend on the round Earth. This would trigger a collapse in technology, communication, transportation, and medicine, reshaping civilization itself. If the Earth were flat, biological rhythms such as circadian cycles, seasonal changes, and ecological patterns would be disrupted. Circadian rhythms are tied to the 24-hour cycle of light and dark, which is explained by Earth's rotation on its axis. A flat Earth would alter how day and night are distributed, potentially producing irregular or uneven cycles of light exposure. This would disrupt the internal biological clocks of humans, animals, and plants. Seasonal rhythms, which depend on the axial tilt of a spherical Earth orbiting the Sun, would not exist in the same way. Migration patterns of birds, hibernation cycles of mammals, and breeding seasons of many species depend on predictable changes in daylight and temperature. Without spherical Earth mechanics, these patterns could not be explained or sustained. Marine life follows tidal rhythms influenced by the Moon's gravitational pull on a spherical Earth. A flat Earth would not account for the same tidal dynamics, disrupting feeding cycles, reproductive timing, and navigation in ocean species. Plants also rely on photoperiodism responses to lengths of day and night to determine when to flower, grow, or go dormant. Human health is regulated by circadian rhythms controlling sleep, hormone release, and body temperature. Jet lag, shift work adaptation, and seasonal affective disorder are all tied to the spherical Earth's rotation and orbit. If Earth were flat, the predictability of these natural rhythms would vanish, leading to biological disorientation across all forms of life. Thanks so much for watching. I really appreciate you spending your time here. If you enjoyed this, feel free to check out more videos for even more interesting topics. See you in the next one.